Hi everyone, I am glad to have the opportunity to deliver the research result of our group. The formation and the layer density control of indium nitride nanoducts by plasma-assisted molecular beam epitaxy via droplet epitaxy technique. My advisor is Professor In-Sung Yu. I am Hugo, the junior undergraduate student of National Donghua University, Department of Materials Science and Engineering. Here is the outline of this talk: introduction, experiment method, results and discussions, and conclusion. Introduction. First, we need to know what is the quantum dots. Quantum dots are quasi-zero-dimensional nanoscale materials that have the property of quantum confinement. So we can stimulate quantum dots and then let it emit electronic magnetic waves. The wavelength is related to its component and dot size. If the dot size is big, it will demonstrate redshift. If dot size is small, it will demonstrate blue shift. Quantum dots have the advantage of its small size and high emitting efficiency. So for those uniquely physical properties, there are many applications of quantum dots. For example, fluorescence probes in cell labeling, quantum dot memory, quantum dot display, and quantum dot laser. Instead of electronic devices and biomechanics, there are still many fields of quantum dot could have the potential to achieve, such as environment, renewable energy, food agriculture, and so on. So after realizing the significance of quantum dots, it is a vital important thing we must concern. How can we fabricate quantum dots? Currently, there are several methods we can choose: chemical collider method, lithography and etching method, and self-assembly method. This method is suitable for MBE or MOCVD. In this method, there are two growth modes. SK mode, through stress relaxation when lattice mismatch, the quantum dots will nuclear and grows by itself. Droplet epitaxy. The concept of droplet epitaxy was proposed by Hugo J and his co-worker at the first time in 1990. They separating 3-column and 5-column enemies in MBE chamber. So there are two processes: droplet in metallic droplet formation and nanodot formation. The advantage of quantum dot are layer free and can be employed on a larger substrate. Experiment method. We use plasma-assisted molecular beam epitaxy system to produce our materials. It is a K-cell with three-group solid source, and the radiation frequency plasma with pure nitrogen. We use hydrogen fluoride to remove the oxide on the substrate, then put it in MBE chamber, thermocooling for 1 hour at 850 degrees Celsius. Pre-nitridation for 40 minutes. This process is optional. indium droplet formation for 30 minutes, or 30 seconds, sorry, and nitridation for 30 minutes, annealing for 10 minutes. The read analysis is fabricated, is employed in every stage. Results and discussions. In situ read analysis, read is acronym of reflection, high energy, electron diffraction. After thermal cooling, the reconstruct silicon surface is streaky, you can see here. And after pre-nitridation process, read analysis will turn into foggy because of very thin amorphous silicon nitride film deposit on the substrate. Indium droplet formation, the read pattern becomes spotty and foggy because the film getting to rough, and indium nitride nanodust formation, you can see the debye ring here. It is attributed to its random orientation of indium nitride nanodust. Annealing, following with annealing, the read pattern does not change. The characterization of indium droplet and indium nitride nanodust. Here is the SEM image of indium droplet and the indium nitride nanodust, respectively. The indium droplet will, when indium atom contact to substrate, it will grow by itself, self-organize. So the density of indium droplets is 1.34 times 10 to the 11th power. The density of indium nitride droplet, indium nitride nanodust, is 2.21 times 10 to the 10th power. AFM image in amplitude and light scan of sample surface. Figure A is indium droplet and figure B is indium nitride nanodust. If you see the AFM image in amplitude here, you may find that the density of figure B is smaller than figure A. So it tells us after we do the nitridation process, the density will decrease. And here is the Roomin square value. It implies the surface roughness and the height of the surface roughness and the height will increase after we do the nitridation process. The XPS analysis, the signal of indium nitride is come from the pre-nitridation process. So you can observe the figure B, the asymmetry of indium 3D 5/2 and indium 3D 3/2 orbital is asymmetry here. It is because the indium nitride signal in figure B. So the XPS spectrum can also support the SEM analysis we mentioned above. Cross-section TN image of indium nitride nanodust. There is indium nitride nanodust you can see here. A dome-shaped indium nitride nanodust and it is 15 nanometer in size, and its height is around 10 nanometer. A very thin silicon nitride film between silicon substrate and the indium nitride nanodust is come from the pre-nitridation process. So according to the analytic data we mentioned above, we graph the schematic diagram of indium nitride nanodust formation After thermal cleaning, we do the pre-nitridation process. So a very thin silicon nitride film deposits over the substrate. Then indium droplet formation via absorption, surface diffusion, and nucleation among indium atoms. Also, the aggregation, also the disruption phenomenon will happen at the same time. Then nitridation. Indium atom surface diffusion and react with nitrogen atom to form indium nitride nuclei. So the lower density and bigger size indium nitride droplet will form because the aggregation, surface diffusion, and the disruption phenomenon also occur. After we realizing the characterization of indium nitride nanodots, we want to know how can we control the density of indium nitride nanodots. There are two factors can control. First, substrate temperature, and second, the pre-nitridation process. And here is the SEM image in different substrate temperature. We plot of size and density distribution of indium nitride nanodots as a function of substrate temperature. So you can see the blue line is the density of nanodots, and then the black line is the diameter of nanodots. With increasing substrate temperature, the diameter of nanodots is increasing, while the density of nanodots is decreased. The effect of density with pre-nitridation process. The red point is the density. We do not carry out the pre-nitridation process. So you can find if we do with the pre-nitridation process, the density will decrease compared to we do not do the pre-nitridation process. So it implies the surface condition also affect the nanodot density. The AFN image and the line scans. You can see here, with increasing temperature, the roughness of surface is increasing also. If you see the line scan analysis here, you can find the aggregation phenomenon is happen obviously at higher substrate temperature. The XPS spectra in indium 3D and a silicon 2p orbital. The signal of indium nitride binding is getting lower when substrate temperature is relatively high. It is the indium nitride signal. There are two factors can explain this phenomenon. First, due to lower density and higher particle size of nanodots at higher substrate temperature, the reaction area will become small. So the weak indium nitride signal will be at higher substrate temperature. Second, the probability of indium nitride disruption is higher at high substrate temperature than at lower substrate temperature. The proportion of nanodots coverage is decreased with higher substrate temperature. So the weak silicon nitride signal, so the relatively stronger silicon nitride signal will become at higher substrate temperature. The model of effect for growth in different substrate temperature. The figure A is Indian droplet formation at lower substrate temperature, and figure B is Indian droplet formation at higher substrate temperature. At high substrate temperature, the phenomenon of surface diffusion, aggregation, and disruption is happening. The probability of the mentioned phenomenon is happen. The probability is happen larger than at a lower substrate temperature. So the relatively big dot size and lower density of nanodot will formation at high substrate temperature. Conclusion. The self-organized Indian nitride droplet, Indian nitride nanodots have fabricated on silicon substrate by PA-MBE via droplet epitaxy successfully. With the increasing substrate temperatures, the density of Indian nitride nanodots will decrease, but the dot size of Indian nitride nanodots will increase. If we carry out the prenitridation process, the density of Indian nitride nanodots is lower than the process without the prenitridation process. The density of Indian nitride nanodots becomes lower, but the dot size of nanodots becomes higher due to the more apparent aggregation phenomenon and disruption of atoms for growth at higher substrate temperature. Acknowledgement. We would like to thank to Ministry of Science and Technology for financial supporting in this study. Michael Chen and Stanley Wu of UVAC Taiwan for the MBE maintenance. Dr. Chen for the preparation of PN samples. Thanks for your kind attention.
Thank you. So, the paper question.
Can you remind me the size of the droplets and of the height of the nanodots?
Yeah.
What was the size of the droplets?
You said
Indian droplets.
the size of Indian droplet?
Roughly.
Roughly around 10 nanometer.
10?
Yeah.
And the nanodots? How high are they?
Around 50 nanometer. Yep.
Thank you.
Some questions? Have you checked the fluorescence efficiency of your dots?
Or not yet.
Yet?
We try to let a nanodot have the property of quantum confinement, so it could become quantum dots. But it is the next step we want to do in the future.
Also, you have explained that the color of the emission wavelength is clearly due to the size of the dots. So you will have to tune finely if you want to define or to obtain the right wavelengths. You will have to tune the size of the dots.
Yes, if the dot size is, if we can fabricate a different dot size in the substrate, then the continuous spectrum is shown. It is our expectation.
Okay.
But it is tough to do.
I would like to complete, because the droplets are so small, 10 nanometer droplets, yeah? So maybe it would be more clear to use the name nanodroplets. That's the name, yeah? Because are of nanometric size, so you can call them nano droplets.
Yeah.
It will be better. That's the comment.
Okay. So let us thank again our speaker.